This lesson is for 4.6, Introduction to Systems of Equations. Our essential questions are: what is a system of linear equations, and how do you find the solution to a system of linear equations? So example number 1 says a system of equations is a set of two or more equations. Consider the following system of equations. So we're giving two separate equations and they are both in standard form. They're asking us to graph this system of equations on the coordinate plane. Previously this week, I mentioned that a system of equations is simply more than one equation graphed on the same coordinate plane. So today, what they're asking us to do is graph those two equations. So since they're both in standard form, you could technically find the x and y intercepts and graph that way, or you could put them both into slope-intercept form and graph using that method. So if we put them into slope-intercept form, line 1, I would first minus 2x from both sides. And I could not have a negative in front of y, that's an understood negative 1 that we would need to go through and divide everything by, which would just change all the signs. And so line 1's equation in slope-intercept form would be y equals, I'm going to put the x term first, that would be positive 2x, and then that turns out to be plus 5. If we solve the equation for line 2 for slope-intercept form, we would minus 2x on both sides, and if I write it in the proper format, the equation is y equals negative 2x plus 1. So when we go to graph, if we graph equation for line number 1, and if we're using the slope-intercept form method, we will start with the y-intercept, so I will put a point at 5. And whenever our slope is a whole number, we have to remember there's an understood 1 underneath. And so it's a positive 2x, so I can go up to right 1 several times. To make more points in the opposite direction, I could go down 2 back to the left 1. The more points that you make, the more accurate your line will be. So it's very helpful if you make as many points as possible, specifically if you're graphing to solve. And obviously, if you're doing it by hand, that's going to be very important. So we've got our first equation, our first line. And so when we graph the second one, we're going to need to start with the y-intercept as well and use our slope to find the point of intersection. So if we graph the second equation, we've got the y equals negative 2x plus 1. So this time we're starting at a y-intercept of positive 1. And if our slope's negative 2, we should go down to right 1, or we could also have gone up to back to the left 1. So I can do that repeated pattern both ways to make as many points as possible and make a really accurate line. And then once you have as many lines as you can make, or at least, as many points, sorry, or at least enough to make it look very accurate, you can sketch your graph for your other line. And so the solution to any system is the point of intersection. So for this particular system, the point where they're going to intersect is this ordered pair, negative 1, 3. So this point of intersection is negative 1, 3. So the solution to this system is negative 1, 3. Now what that means is that I should be able to substitute in that x value and that y value into both equations and it will make both of them true. So I can use substitution to check and see if I am correct. So I'm going to substitute these x and y values into the equations. I could use the slope-intercept form. I could use the original one. It doesn't matter as long as they're both equivalent. So if I check the first one, I would have 3 equals 2 times negative 1 plus 5. So 3 equals negative 2 plus 5. 3 equals 3. So it works in the first one. If I were to check for the second one, I would have 3 equals negative 2 times negative 1 plus 1. So 3 equals 2 plus 1. 3 equals 3, it works in the second one. So if they ever give you some ordered pairs and ask if it is a solution to the system, you must be able to plug that ordered pair into both equations, and it has to make both equations a true statement. So they're asking us what we notice about the point -2, 5. So let's look at the point -2, 5. So -2, 5 is on the equation of line 2. So it is a solution to the equation for line 2. So it is on line 2. So it is a solution for equation 2. So if a point is on a line, that means it is a solution to that equation of that line. That is why if a point is a solution to a system, it is one that works in the equations for both lines. So then they ask us, what do we notice about the point -1, 3? So -1, 3, that one is on both lines. So it is a solution to both equations. So if we check out the point 1, 7, we've got 1, 7. That is a point on line 1. Oops, sorry. That is a point on line 1. So it is a solution to equation 1. And then what do you notice about the point 1, 1? So 1, 1 is not a point on either line. So it is not a point on either line. So it is not a solution to either equation. So again, if the point falls on the line, it is a solution to that equation. If the point is a point that falls on both lines, which must be where it intersects, then it is a solution to the system. So let's practice number 1 is telling us to consider these two equations. And it says complete the following sentences. So the ordered pair -2, 5 is a solution to, well, if we look back, when we were looking for determining if it was a solution, what we just did is I plugged that point in to each equation. So what we're going to do is plug that point in to each equation to determine if it is a solution to line 1 and line 2. If it happens to be a solution to both, it is the point of intersection. It is a solution to the system. So if we plug in those x and y values, so I'm going to have 5 times x plus 2 times y equals 8. And then -3 times x minus 2 times y equals -4. And see if it makes either one of them true. So our x values are -2 and our y values are 5. And so if we work them out, line 1 would come out to be -10, and then that's plus 10 equals 8. So -10 plus 10 is 0 equals 8. Well, that's not true, so no, it is not a solution to line 1. So let's check out line 2 and see if that's correct. So -3 times -2 would give us a +6, and -2 times a +5 would give us -10. And that's all supposed to be equal to -4, so 6 minus 10, -4 equals -4. So yes, it is a solution to line 2. Now if it had worked in both, it would be the solution to the system. So then at point 2, -1, so same two equations, we're going to try 2, -1. So going to set it up again, and I'm going to substitute in 2 and -1 and see if those, if that point works in one or both equations. Okay, so again, we're testing 2, -1. So 2 is the x, -1 is the y. So our x values are +2, our y values are -1. And so on equation line 1, that will come out to be 10 minus 2 equals 8. That's true. On equation number 2, that comes out to be -6 plus 2 equals -4. That is also true. So that point works in the equations for both lines. So that is actually the solution to the system, because it is a solution to line 1 and it is a solution to line 2, and it specifically is the solution to the system of equations. So technically it is all three. But very importantly, I need you to understand that if it is a solution to both lines, it is a solution to the system. So we're going to check the ordered pair 0, 4 now. So if we go back and we check 0, 4, we've got our x's and y's are going to be replaced with the coordinates, and we're going to see again if that point is making either one of them true or both of them true. So at this point, we should be able to reason that if it's two lines and they're not the same line, there should only be one point of intersection. So realistically, this other ordered pair should not work in both equations. So we're going to check it out and see. So x value, y value, so our x's are 0, our y's are being replaced with a 4. So the first one comes out to be 5 times 0 is 0, and 0 plus 2 times 4 is 8, equals 8, so it works in this one. -3 times 0 is 0, and -2 times 4 is -8, equals -4. That does not work. So it is only a solution to the first line. So it is a solution to line 1. So because I had already found the point of intersection, if I think about a system, if I think about two lines on the same graph, if they're both lines, they should never double back and intersect more than once. Now there are two special scenarios, but if they're just two lines intersecting, they should never intersect more than once. So is there ever a time when a system of equations will not have a solution? If so, sketch an example. Okay, so if the solution to a system is the point of intersection, we have to think, well, what kind of lines never intersect? Okay, well, hopefully you're thinking about parallel lines. So if two lines are parallel, they will never intersect. So this would have no solution. Eventually, we're going to talk a lot more about how we could tell before we ever even graph two equations, and we've had a little bit of that discussion already. If we have two equations and they're both in slope-intercept form, like y equals 3x plus 5 and y equals 3x minus 2, parallel lines will always have the same slope, but they must have different y-intercepts. So for them to be parallel and have no solutions, if my equations are already in slope-intercept form, I can see by comparing the slopes and y-intercepts to see if they're going to be parallel. So if instead of having the same slope and different y-intercepts, if they had the same slope and the same y-intercept, so if I solve for y and I have two of the exact same equations, well, on a graph, that ends up being the exact same line graphed on top of itself. So this is another special situation. So if the point of intersection is a solution for a system, and if I graph the same line on top of itself, it is going to intersect, they're going to intersect each other infinitely, forever. So there are infinite solutions if we find that our equations are the same, or even if we aren't solving for y and for whatever reason we choose a different method of graphing, if you come out to have the graphs matching and it's the same exact line, it is infinite solutions. So considering this following system, it says to sketch the graph of the system of equations. So again, you could technically plug in 0 for x and plug in 0 for y and find the intercepts to graph that way. Or you could put them in slope-intercept form and graph that way. So we're going to put them in slope-intercept form and see if we can make some observations. So for the first equation, if I solve for y by minusing x and then dividing by the -1 in front of y, the first equation ends up being y equals a positive x minus 3. On the second equation, if I add 2x to both sides and I divide everything by a positive 2, my second equation ends up being y equals positive x minus 3. So when we solve them for y, what do you notice about both equations? Well, they're the exact same equation. So we just talked about this. So if I go to graph this, and they're both y equals x minus 3, I'll do them in different colors so we can see here. If I graph the first one, I'm going to start with my y-intercept of -3. And if my slope just looks like an x and it's positive, that's an understood positive 1. So it's going to go up 1, right 1 every time, or down 1 to the left 1. So we have our first equation. So there's the line. And so when we go to graph the next one, it's the same exact thing. I'm going to start at -3, go up 1 over 1 every time, or down 1, back 1, and it ends up being the same line on top of itself. So for this particular system, there are infinite solutions. So for any system of linear equations, there are 3 possibilities. They can either intersect once, intersect not at all, or intersect infinitely. So we're either going to have one solution, no solution, or infinite solutions. So if we try example number 4, consider the following system of equations, sketch the graph of the system of equations. Okay, so let's solve them for y, see if we can compare them. So on the first one, I'll minus 4x from both sides, divide everything by the coefficient of 3, and so y equals -4 thirds x. 3 over 3 will make that a plus 1 at the end. So I will start at +1. If my slope is -4 thirds, that means I go down 1, 2, 3, 4, and over 1, 2, 3. Or I could do the reverse and go up 4, 1, 2, 3, 4, and go back 3, 1, 2, 3. And so you could continue to do that to make more accurate points. Let me double check that. 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3. Okay, so we have our first line. Need to be as accurate as possible. I know mine don't look super clean here, but you need to make sure that you're doing it as accurate as possible. If you have a ruler, that's very helpful, because you have to see the exact coordinate where these lines would intersect if they do intersect. And so if we solve the second equation for y, we minus 2x from both sides, and we divide everything by -5, we end up with y equals a positive 2/5 x plus 1. So we can already see that they're different slopes, so they're definitely going to intersect. They're not the same line, they're not parallel, so it must be a one solution kind of situation. So I have a y-intercept at a +1, and my slope is up 2 to the right 5, 1, 2, 3, 4, 5, or I could go down 2, back 5, and sketch my other line. So we could have also observed that because the y-intercepts are the same, that must be the point of intersection. So the solution to this particular system is that ordered pair where they're going to intersect, and that is the point 0, 1. So this point is a solution to both equations independently, and it also is a solution to the system. So now we are to beat the test. It says consider the following system of equations, sketch the graph of the system of equations. So same as we've been doing, you could either find the x and y intercepts, or you could solve them for y and compare, make a judgment, and then put them on the graph. So if I solve the first equation for y, that comes out to be y equals negative x plus 5. Since it's just negative x, that means the slope is -1 and the y-intercept is a positive 5. So I should have a starting point at 5, and I'll go down 1, right 1. Because it is a negative slope, it should be going downhill. It should not be going the opposite direction. So I have a negative slope line. Okay. And then when I solve the other equation for y, we would first minus 2x. But we would have to come back and divide everything by -1 because it says negative y. So that comes out to be y equals a positive 2x plus 2. So starting at a positive 2, and if my slope is 2x, if my slope is 2, I got to remember it's over a positive understood 1. So it goes up to right 1. Make a couple points here. You could go down 2, back 1. And we can already see our point of intersection being as accurate as possible so that we get the correct answer. The point of intersection for this system is the ordered pair 1, 4. So that is the solution to the system. So 1, 4. Part C says create a third equation that could be added to the system so that the solution does not change. Graph the line on the coordinate plane. So this is pretty open-ended. I mean, there's a few number of equations that make sense, but there are really a whole lot of equations that you could write as long as it's an equation of a line that goes through this particular point. It has to be an equation where 1, 4 is a solution to that system. So if we went the easy route, we could really draw some special case lines, which would be like some horizontal or vertical lines. So if I were to draw a horizontal line that went through this ordered pair, the equation of that line would be y equals 4. Because the slope of a horizontal line is 0, and the y-intercept of this particular one is 4, so that comes out to be y equals 4. If instead we did a vertical line, which is not a function, but it is a line, and we wanted it to go through this point, it would have to go through when x is positive 1. And so the slope of this line is undefined, but the equation of a vertical line is x equals the x-intercept. So the equation of this vertical line is x equals positive 1. So we also could have come up with a diagonal line that also went through the point 1, 4. So if we want to do that, we'll try one last option here. So let's see, get a different color maybe. So say that I want to make it go through the point 1, 4. So that's an x and a y value. And let's just say that it also goes through the point, so 1, 4, and let's say it also goes through the point -1, 2. For this equation of this particular line here, I really just made the slope go down 2, back 2, so that really ends up being a slope of positive 1 with a y-intercept of 3. So even if I were to find my slope from using these two ordered pairs, I would say 2 minus 4 over -1 minus 1, which would give me negative 2 over negative 2, so my slope is 1, and I can clearly see my y-intercept's 3. So if I wanted to pick a more challenging line, I could have just really used 1, 4 as one of the ordered pairs and made up a slope, made another point. There are several different options. For this pink line that I just made up, the equation would be y equals 1x, or just x, plus 3. So that one would go perfectly through that point. So we made up 3 different ones that would go through there. So question number 2, two linear functions in a coordinate plane have no points of intersection. Which pair of functions does not intersect? So we just had this discussion about how parallel lines have the same slope but different y-intercepts. So really looking through here, all of these options, well, sorry, let me fix what I'm saying. The first 2 options are all in standard form, and then options C and D have one equation in standard form and one equation in slope-intercept form. So we could go through and solve them all for y, that is an option, or we could really see that if the coefficients of x and y are the same on both equations, or if they reduce to the same thing, that we will have a similar slope. So we'll do one like the long way and kind of derive that formula or that shortcut for if they're both in standard form, how can I compare their slopes? So on this first example, I would minus 6x from both sides, and so I'd have 2y equals negative 6x plus 12. I want to divide everything by 2. Y equals negative 3x plus 6. The second equation, we would minus 20 from both sides. So we would have 10y equals negative 20x plus 14. And then we would divide everything by 10. Y equals negative 2x plus 1.4. 14 divided by 10 is 1.4. So this particular example, we have different slopes and different y-intercepts. These are going to intersect. But I did this because I wanted to also go back and say, well, when I found this value, let me go back. When I found this slope value, it ended up being negative a, the number in front of x, divided by b, the number in front of y. So when you have standard form, ax plus by equals c, we actually wrote this in our notes in the back of the book the other day, we can find the slope by doing negative a over b. So let's try it for option 2. So if 4 is a and b is a positive 2, we could find the slope of this first one by doing negative 4 divided by 2, which comes out to be negative 2. And we could find the slope of the second one by doing negative 20 divided by 10, which comes out to be negative 2. So far our slopes are the same, but we're specifically looking for where the functions do not intersect. So if our y-intercept also happens to be the same, then it will be an infinite solution situation. So let's go back and kind of look at how we got that y-intercept. So in the first set, that y-intercept, that n value that we derived by solving for slope-intercept form, this came from c divided by b. So they came from 12 divided by 2, the 1.4. The 1.4 came from c, the constant, divided by b. So the y-intercept, when they're in standard form, can be found by the constant divided by the coefficient of the y. So if we're trying this shortcut on option B here, we would have that the y-intercept can be found by 12 divided by 2, so it's 6. For this particular version, the y-intercept could be found by 30 divided by 10, so it's 3. So for option B, I just found out that they have the same slope, but they have different y-intercepts. So these are going to be parallel lines. So B would never intersect. Now, if that shortcut is too much for you when it is in standard form, you are more than welcome to just solve for y, put them in slope-intercept form, and compare them. Simply trying to teach you these shortcuts for when you're on time test and you need to move quickly, that is something that you can do. So if we go back just to check the last two options just to be sure, if we were to find the slope and y-intercept of the first one since it's in standard form, so our slope would be -6/2, so that's -3, and our y-intercept would be 12/2, which is 6. So different slopes, different y-intercepts, these are going to intersect. On the last one here, again, slope is from -a/b, so -10/10 is -1, and the y-intercept is from c/b, so 6/10, which would come out to be 0.6. So it does have the same y-intercept, but it has a different slope, so it is going to intersect at one point. So option B is the only one that produced a pair of parallel lines that would not intersect. So there's the other particular relationship that I want to take a second to discuss from this example. We know that parallel lines have the same slope, and we have covered this a little bit in the past, but not very thoroughly. So we need to make a note here that parallel lines, if you have not already done so, parallel lines have the same slope, but different y-intercepts. And then we also need to really talk about perpendicular lines. So perpendicular lines, if you don't remember what that means, perpendicular lines are when two lines intersect, but they form four right angles, so four 90-degree angles. So perpendicular lines also have a special relationship. So perpendicular lines, if we were talking about a system, clearly only have one solution because they have one point of solution, one point of intersection. But there's something that we can tell from the slope of two separate equations. We can tell already before we graph that they're going to be perpendicular. Now, perpendicular doesn't mean all intersecting lines. Specifically, it's the ones that intersect and form 90-degree angles. So perpendicular lines have what we call negative reciprocal slopes. So for example, if one of my equations was y equals 2x plus 4, to know if the other one was perpendicular, I would have to have the reciprocal, which if it's originally 2/1, it would have to be 1/2. But also, this word negative reciprocal means it has to be the opposite sign. So if this was a positive 2/1, this would have to be a negative 1/2. Now the y-intercept could be the same, it could be different, it doesn't matter. The thing that tells me that it's going to be perpendicular is specifically if my slopes are negative reciprocals of each other. So we'll do a couple more examples. So if I was given y equals 3/4 x, y equals -3/4 x plus 8. A perpendicular line to that is going to have to be y equals 4/3 x plus or minus anything, it doesn't really matter. But specifically, if my slope was negative this time, it has to be positive this time. If it was 3/4, it has to be 4/3. So parallel, those are pretty easy. Same slope, different y-intercepts. Perpendicular, the y-intercepts are not really the concern. It's the fact that the slope is the reciprocal of each other and that it also has opposite signs. So if it was -3/4 and -4/3, they would not form a perpendicular set of lines. So the last thing you need to add to your notes is mostly a little bit of vocabulary. there's some terminology that we can use for the different scenarios that occur with linear equations, systems of equations. So basically, if our two lines intersect at one point, they are considered to be consistent and independent. So consistent essentially means it has a solution, and independent means it is two separate lines. If our system of equations comes out to be the same line and it has infinite solutions, it is consistent because it has a solution, but it is dependent, which means it's the same line. So again, consistent means it has a solution. Dependent means that it is the same line. So the last scenario would be if the system is inconsistent, and that's only going to happen if you have parallel lines. So inconsistent means it has no solution. So consistent means it has a solution, inconsistent means it does not. Independent means it's two separate lines. Dependent means it's the same line. So we could also technically say that a set of parallel lines is inconsistent and independent because it is two separate lines, but more importantly, it does not have a solution.